Now we're going to have a look at the area between two curves. It's a little bit different from the area under a curve, that is the area between the curve and the x-axis, but the principle is exactly the same. So let's pursue it and see what we can find out. Ladies and gentlemen, the area between two curves involves exactly the same procedure in principle as that used to find the area between a curve and the x-axis, from say x is a to x is b. We use the rectangles to ensure that we always get a positive integral, and I'll show you a little diagram to illustrate what I mean. Here we've got one function f1 of x and another function f2 of x, and we are required to find the area between those two curves from x is a to x is b. Okay, now here's our rectangle, and we can see that f1 of x minus f2 of x, that is this value here, this y value here of f1 of x minus the y value of f2 of x at, say for example in this case a, where x is a, gives us a positive result, okay? Top minus bottom in terms of y gives us a positive result. And we also know that in terms of the x, if we're integrating from left to right in the positive x direction, as you would see on a number line, therefore our delta x, the widths of our rectangles, will be positive. So therefore in this instance we have a positive height and a positive width, and therefore we know that our integral, as shown there, will be positive. So the area is equal to the integral if we integrate it in that way. Alright, guys and gals? Let's do an example now. We've got to find the area enclosed by the parabola y equals x squared and the line y equals minus 2x, okay? Firstly, we need to find the points of intersection between the two functions, and we'll do that algebraically. So, if x squared equals minus 2x, then we solve that in the usual way. We know that x into x plus 2 equals 0, therefore x would be 0 or x would be minus 2, and that is consistent with what we can see on our graph. Yes? Looks good, doesn't it? Now I've drawn a little rectangle there to just hone in on what we need to do to get a positive integral for this enclosed area shown there in pink, okay? By drawing the rectangle as shown, now have a look up there, there's the top. Why top? I've written that, colour-coded that red, because the top of that rectangle coincides with the y value of the red drawn line, that is y equals minus 2x, yeah? And the bottom of that rectangle, y bottom, as I've called it, coincides with the blue function, the y value of the blue function, which is y equals x squared. So, guys, we need to basically integrate that, and as I'm showing you here, we're integrating it from left to right to get positive x's. So, we need to realise that this expression here will give us a positive integral. Y of the red function minus y of the blue function represents top minus bottom in terms of y for my rectangle, and it gives me a positive height. If I integrate that from minus 2 to 0 with respect to x, I get a positive integral. And there it is. I've left the colour coding in place so that you won't get confused with what I'm doing. Okay, that's minus 2x, that's the top value of y, minus x squared, which is the bottom of value of y for any given value of x, okay, for any given value of x. Okay, let's go for it. We can see that that's what we're doing now. We've got minus x squared after we integrate, minus a third of x cubed, and we're going from minus 2 to 0. So let's just go through the motions now. The 0 terminal here just gives us 0 results. With the minus 2, we've just got minuses all over the place here, guys. We've got a minus there, and we've got negative minus 2 squared minus a third of negative 2 cubed. So just be a bit careful with the negatives because we're getting blizzards of negatives everywhere. So basically, be careful. Now that gives us a net result of minus 4 on 3 inside the bracket, but there's already a minus outside the bracket. So thankfully we get a positive answer, which was what we were expecting anyway. We get plus 4 on 3. Yes? Alright, that is our area between those two intersection points, between those two curves. Easy, isn't it? Now, example 2. Find the area bounded by the lines with equations y equals x squared, that's the blue curve shown there, and y equals 4 minus x squared, which is the upside down quadratic, which you can see drawn in red. Okay, so we want the green area in between them, and we need it as an area. Okay, we're going to make sure it comes out positive when we integrate. So first of all, again, we need the points of intersection between the curves, guys and gals. So let's do that. If x squared equals 4 minus x squared, we've got 2x squared equals 4, x squared equals 2, and therefore x would be plus or minus root 2. Woohoo! Plus or minus root 2. Well, that's looking all right. And there is a very unfortunate looking rectangle. I don't know what happened there. So let me just redraw that just a moment. That's better. The wonders of technology. So I've got my rectangle back again where it should be, and it's enclosed between the two curves, not like it was before. And we can see now that for any given value of x, the top of the rectangle is the y value of the red curve, and the bottom of the rectangle is the y value of the blue curve. Okay, so we're all set to go now. We know that if we're going to integrate from left to right, our delta x's will be positive as well, don't we? Of course we do. Now, so therefore, in order to get a positive integral, we need to do this. We need to go from minus root 2 to plus root 2 in the x department, and we need to go y red or y top minus y blue or y bottom, as I've colour-coded these functions, yeah? So putting that into the actual maths, we've got this minus this. I'm still maintaining the colour coding just to make sure you understand what I'm doing. Yep. Okay, that gives rise to 4 minus 2x squared integrated with respect to x from minus root 2 to plus root 2, and we're ready to go. Let's do the integration. There it is. 4x minus 2/3 of x cubed. Okay, from minus root 2 to plus root 2. Now let's sub in. So we get that subbed in. And then when we fiddle around with that, I won't bore you with the algebra, we get that, which gets to that. Wow. Isn't that great? That is the answer. Yes? Peachy keen. Now there is an NB, which I could add to the end of this, or a PS, or whatever you want to call it. If you want to have less work and the potential for less or fewer mistakes, then what we could have done is we could have looked at the symmetry of this diagram and realised that as far as the left-hand side of the y-axis is concerned and the right-hand side of the y-axis is concerned, we've got a symmetrical situation. So therefore, we could have integrated from x is minus root 2 to x is 0 and then just doubled the result. This works from symmetry, as I say. And it's always nice when you have one of your terminals equal to 0, because it just creates lots of zeros and less work, okay? Which is a good thing to bear in mind. Again, a speedy thing to do in an exam setting. Alright, our next example here is example 3. We've got to find the area enclosed by the functions f of x equals minus x cubed, which is the blue line you can see, and g of x equals minus x, which is the red line. Now this is an interesting one because we've got a flip-flop situation here. Okay, the red is on top to the left of the y-axis and the blue is on top to the right of the y-axis. So we need to be careful what we do with this question. We'll find the points of intersection of the two functions first. So if minus x equals minus x cubed, we know therefore that x cubed equals x, and solving that in the usual way, we would do that, and therefore that, and we would get, by the null factor law, x would be 0 or plus or minus 1. And that looks consistent with what we can see on the graph, so it's looking good, isn't it? Now let's go ahead now and draw our rectangles, just to keep ourselves on the straight and narrow. Alright, there's two likely little suspect rectangles for us. And you can see there on the left-hand side of the y-axis, I've got the red one is on top, the blue one is on the bottom. So in that case, we need to go red minus blue for top minus bottom for any given value of x. And on the right of the y-axis, it's the other way around, as I said before. The blue one's on top and the red one's on the bottom. So we've got to be careful what we do here. Of course, we'll integrate from left to right to keep the delta x's, or the widths of our rectangles, positive. So, as I've said there, red is on top to the left of the y-axis, and blue is on top to the right of the y-axis. So what do? What do we do, guys and gals? Well, hence for a positive integral for both regions, we've basically got to do it like this. The area on the left of the y-axis is y top minus y bottom, which gives us a positive y, or height of the rectangle, times the width delta x. And to the right of the y-axis, we've got y top is the blue function, minus the red one, which is on the bottom, okay, with respect to x. So if we now plug in the values of those functions, we get this. Okay, have a look and see whether you agree with me. Yes, that's looking good as far as I can see. All right, now let's take that a step further, and we get that. Now, there's minus signs all over the place here, so just be careful and make sure we're on the straight and narrow. You see, this is a plus x cubed minus x. That's what I got for the first one. And this is a plus x minus x cubed. So it's like, you know, they're dancing around all over the place here with their pluses and their minuses. But now it's just left for us to evaluate that now, ladies and gentlemen. And I have done that all there, and just proceeding right along. If you trust me, I did evaluate that and I got plus a half. Yeah, so that's how you do it. That's how you do it, guys. Now there's an NB over the page. So let's just go over the page and have a look at what I wanted to say. Again, for less work and fewer mistakes, you could look at the symmetry of this in method A. There are two methods that I've given you. You could use the symmetry and calculate the area on one side of the y-axis only and then double the answer, okay? So, secondly, with CAS, you could just work out the absolute value function of, say, the left-hand side bit of it, which was top minus bottom, that's red minus blue, but the absolute value of that, and then you then evaluate the whole thing from -1 to 1, because you're never ever going to get a negative value of top minus bottom, even though they flip-flop, because you have the absolute value function in there to make sure that the result of taking one from the other is always going to be positive. Okay, so that's really the best way to go if you had a CAS, yeah? That's right. So, very exciting. Let's go on to the next one now. Example 4, this is a tricky one, just to mix it up a little bit for us. What have we got here? The functions y is sine of x over 2 and y equals cos of x over 2 in the region shown. And we want the yellow bit. Very nice, isn't it? So we'll have to get the points of intersection, again, of the functions shown. So this is, again, testing our ability to solve trig equations. We know that sine x over 2 equals cos of x over 2 where they intersect. And therefore, if we divide both sides by cos x over 2, we're going to get tan the man. Tan x over 2 equals 1. So we've just got to solve that for the first two occasions that happens to the right of the y-axis. So therefore, if tan of x over 2 equals 1, we know that x over 2 would equal pi over 4, then add another pi to that, etc. Remember, the period of tan is pi. Therefore, x would be exactly double those values, and there that gives us our points of intersection. Rather nice, isn't it? And that's consistent with what we can see on the graph, isn't it? Alright, so now looking at the dreaded rectangles again, there's a rectangle for us, and we can see the top of the rectangle for any particular value of x is the blue function or the sine function, and the bottom of the rectangle is the red function or the cos function, okay? So there's top, there's bottom, and we're going to integrate from left to right in the x department, and we'll be guaranteeing we'll get a positive integral result if we do that, yeah? So you're following right along now because you're getting used to these. Now we've just got to integrate this thingy here now. So var she be, there's the result, right? So now the rest is just Algebra City, USA, and off we go. This looks very interesting. Cos of pi on 4, anybody know what that is? Quadrant what? Quadrant 3, so it's negative, isn't it? And it's the same as cos of pi on 4, so that's going to be minus 1 over root 2, so minus a minus gets plus 2 over root 2 in my reckoning. Same thing with this beastie, because cos and sine are both negative in quadrant 3. So I think the result is going to be like I just thought. So, ooh, look at that. 8 over root 2, or if you want to get all fancy and rationalise the denominator, 4 root 2. But you don't have to do that, as I told you, ladies and gentlemen. All right, one last example for us. Hang in there, guys. It'll be worth the effort. In this case, we've got f of x is log of x minus 1, where x is going from that value there to that value there. In the first part of this question, we have to find the inverse and sketch both the original and the inverse on the same set of axes, showing all key features, including endpoints as coordinates, etc., etc., and we will do that. And in the second part, we've got to use the inverse function to find the exact value of that, which we definitely can't do analytically if that is a log function. Okay, so this is a way of getting around the fact we can't analytically do that. And they do ask this in the methods exam, so you do need to know what's going on. All right, part A today, we've got, we're letting y, I always do that when I'm finding inverses, I let y equal the original. That is the domain, and I'm just checking out what the range is going to be. There it is, because that's going to be the domain of the inverse, okay? So I wanted to work that out. And therefore y equals that, okay? Because the log of 1 is nothing, and the log of e to the 1 base e, of course, is just 1, okay? Funny about that. Now for the inverse, we're going to swap x and y as we always do. And we get x equals log of y minus 1 base e, and therefore e to the x equals y minus 1. Therefore y will be 1 plus e to the x, or e to the x plus 1. Now putting it back into the f notation, as we have to, we know that f to the minus 1 of x equals that. Now I'm just swapping the x's and the y, the domain and the range. So what was the range of the original is the domain of the inverse, and what was the domain of the original is the range of the inverse. All right, now I think we're just about ready to go, aren't we? Yes, let's do the graphs. Okay, so that's the funny looking graph of the original. It's looking pretty non-eventy, isn't it? But I've done everything right, I think. I've put the x-intercept here, and I've put the other endpoint in there as well. Okay? Now let's do the inverse. You just swap x and y and do the mirror image about the line y equals x, which gets us that funny looking beast there. Okay, so this is our f of x, and this one here is our inverse. Yeah, so see how I've swapped x and y? Yes, it looks all right, doesn't it? Let's just check it out and make sure we're right. Yes, yes, it looks all right. Looks good. So let's just go over the page and have a good look at what we're going to do. Here is the graph. Now, you want to watch this, guys, because this is important. Okay, don't tune out now. You need to know what I'm doing. All right, part B is, find the exact value. All right, now look at this. We need that, which we can't do. I'm sure you'd agree. We can't do that analytically. So we're going to have to find a sort of a graphical or a rabbit out of a hat technique using the inverse, which is what we're asked to do. All right, so we can't do this analytically, but we can do it using the inverse. Now, have a look over there. I've got to find A1, which at the moment I'm a bit lost as to know how to do it. But have a look at this. There's A2, okay? Call that A2. This little bit enclosed by the curve, this line, and this line. Now, you know, and I know, that I can work out that rectangular area which comprises A1 plus A2. Okay? So, because we've got the dimensions of the rectangle, this width here is E plus 1, and this height here is 1. Okay? So, therefore, A1 plus A2, so therefore, A1 plus A2 is E plus 1. Now, for my next trick, I'm going to look at the inverse function. Okay, by the symmetry with the inverse function, you can see, ladies and gentlemen, this is the rabbit out of a hat, that this bit here under the inverse, because it's symmetrical about the line y equals x, that vertical bit under that graph will be the same as this horizontal bit, which is also equivalent to A2, right? There, they will be the same areas. The A2s will match, okay? Now, the reason I'm doing that is because it's very easy to work out the A2 from this inverse function, okay? Have a look. So A2 is the integral of the inverse function with respect to x from the x terminals, which are from 0 to 1. This is pretty nifty, isn't it? It's very, very interesting. So that's easy to do. That's why we're doing it this way. So that comes to that, and then evaluating that, we're going to get that, which just simply comes to that, which comes to that. Okay? Now, for the final knockout punch, we can say by subtraction, now we know what A2 is, and we also know what A1 plus A2 is from before. We know that A1 is what we got for the combined rectangular area, A1 plus A2, which was E plus 1 over here, okay, minus what we just got for A2 by fiddling with the inverse function. And therefore the result is just going to be 1. Whoop-de-doo. How do you like that? It's amazing, isn't it? So that is our lesson on areas between curves. Okay, go forth and do plenty of practice, and we'll see you soon.